Raycasting is one of the most powerful tools found in modern game development. Almost every 3D game you've ever played utilizes it to some degree, whether that's Mario or Skyrim or even Halo. Its versatility has enabled game developers to create all sorts of different game mechanics that extend across multiple different genres. So what exactly is raycasting? Raycasting, not to be confused with ray tracing, allows us to get information about the game's physics world relative to a certain location or object by casting a ray and seeing what it intersects with. In more human terms, imagine you have a laser gun and you fire it off. That laser will continue to travel forever until it hits something. When it does, the laser gets a bunch of information about the impact, like the location it hit and the object itself, which in the case of Godot would be the physics body. There's other things it can tell you, but we won't worry about them for right now. Those are the two most important ones. It sounds pretty simple, but that simplicity is what makes it so powerful. Game AIs use it to simulate vision, animation systems use it to dynamically align characters' feet with the ground, shooters use it to simulate high-speed bullets from guns, and there's about a million other applications you can come up with. My favorite example is probably Mario Galaxy, which uses raycasting to align Mario with the ground of the planets he walks on, creating the game's gravity-defying movement system. Almost every single time you're working on a 3D game, there is going to come a point where you want to gather information about the world around you that you don't know beforehand. Raycasting is exactly what lets you do that. Most engines offer raycasting support right out of the box, and Godot is no exception. Godot gives us two options to raycast in 3D, the Raycast node and directly using the physics server, which we'll get more into that later. Both have their strengths and weaknesses. The Raycast node extends spatial, so you can move it and rotate it anywhere in your scene. It has a parameter called cast2, which will let you decide what direction and how far the raycast will travel. In order to actually fire the raycast, you can either call the forced raycast update method, or set its enabled property to true, in which case it'll fire a new raycast every single physics frame. To get the results of the raycast, use one of the methods available on the node. Each bit of information the raycast collects can be accessed using the corresponding function, like getCollider for the physics body we hit, and getCollisionPoint to get the position. There's a few other methods, which I'll put on screen now, to access some of the additional information that the raycast collects that I haven't talked about yet. Additionally, there's the isColliding method, which lets you know if the raycast actually hit something or not. Here's a little scene I made with a cube and a raycast node, with its enabled property checked on so its raycast data automatically updates. The script on the cube makes it change colors if the isColliding method on the raycast node returns true. So if the raycast hits something, the cube changes color, as you can see when I move the sphere up to where the raycast hits it. The length of the raycast is really important. If I change the length of the cast2 property, moving the sphere up doesn't trigger the color change anymore. I have to move the sphere really close to the cube, in which case the raycast will finally pick it up. The raycast node is great when you always want to raycast from the same relative position, like the muzzle of a gun, but it can be really inconvenient to use when the position and rotation of our raycast is constantly changing, or if we want to do a raycast specifically from one point to another point. This is where Godot's second method of raycasting comes in, directly using the physics server. Without going into the nitty-gritty, Godot's physics engine is represented as a server where all the information about the game's physics world is stored. You can access it using getViewport.world.directSpaceState. Here I store that in a variable called space. The server has a method on it called intersectRay, which takes two primary arguments, the start point of the raycast and the end point. So think of this as shooting off our ray/laser off from the start point, and it moves towards the end point until it either A, reaches the end, or B, hits something, in which case it tells us about it. The intersectRay method also has some optional parameters that are helpful, such as exclude, which allows us to define an array of objects we want the raycast to ignore. Going back to the laser example, it'd be like telling the laser to just move right through all the objects in the array like they don't even exist. intersectRay returns a dictionary containing a lot of different values, which you can see on the screen right now, but the most important ones are the ones we talked about earlier, collider, which is the object we actually hit, and position, which is the location where the raycast hit. Here's a script that uses this method to determine line of sight between an enemy and the player in a stealth game. The start point is the enemy's position, and the end point is the player. We create an array including the enemy in the exclude argument, so the raycast will go through the enemy's body. If results.collider is the player, that means the raycast hit them, and the enemy can see them. If it's anything else, that means the line of sight must be occluded by some other object like a wall, and so the enemy can't see the player. That's about all there is to raycasting, and specifically Raycasting in Godot. I would recommend after this looking into some more advanced physics engine concepts like collision layers to help you better take advantage of the full power of raycasts. I'll put some links in the description to the official Godot documentation about that, alongside some other helpful tutorials.